Hey Chris. Yeah, we're having a talk today about synchronous languages and reactive system design, which is a summary paper of sort of three synchronous languages, ESTEREL, LUSTRE, and Signal. So it was published in 1998, and the development of those languages was mostly late 80s. I think ESTEREL was sort of published, or the paper introducing it was published in 1987. So it's a little bit later, and it's sort of comparing these languages. And I think it's an interesting paper because those three languages, the development of them sort of happened all around the same time in France. So Sterol, Lustre, and Signal, I believe, were all sort of developed in France by different universities, sort of independently. I'm sure sharing ideas. And so it's just really interesting to me that around this time, like suddenly synchronous languages sort of sprung up. And this paper, I think, is just like a good compare contrast of them, and gives like a nice little introduction into the notation without going too deep, because they're sort of languages in their own right. It's quite easy to go quite deep into semantics and get sort of bogged down there. Although it is interesting, I think this is like a good sort of light overview of the languages, but also focusing on how they're similar. And I think there's some interesting insights there. And it's also sort of this is all around the same time as state charts, like ESTEREL and state charts, the original state charts, a visual formalism paper were released in the same year. So I think it's very relevant to state charts, um, which is my interest in it. And also just in general, like reactive programming and approaches to reactive programming reactive systems. I think these papers are fairly seminal of these languages, and they are the basis for some of the code we write today, like Elm, the
Mm-hmm.
lucid synchrone, which is an extension of lucid, which I think is related to Lustre. There's
Mm-hmm.
like some connection there of family of languages that come back to these ones, and then Elm is based on lucid synchrone, or it was used to be, and then Flux was based on Elm, and Redux was a Flux architecture.
There's
So
a
Redux,
whole
like you chose Redux like all the
lineage,
way back.
and yeah, I
Yeah,
totally
so this is
agree.
like a lineage. Yes, yeah. So that's sort of like the context, I think, for the paper.
Yeah,
Um,
maybe
that
slightly additional context is some of the work you're doing around creating your own notation.
yeah,
Maybe you want to just touch on that. I think that might help frame this conversation for someone listening, and why you're sort of interested in reading through this particular paper.
yeah. Well, so that is sort of I've been thinking for a while about an extension or sort of a different approach to reactivity. It's building on what state charts did, which I think was really powerful. And I've used state charts a lot, and I think they're great, but I do think there's some issues or things that aren't so great when you start building big systems with them. And so I've been exploring something I'm calling event charts, which is a notation focusing on how events are flowing through the system. And it's essentially a reactive notation. And so these languages, especially Signal or Lustre, there's some data flow
Mm,
synchronous languages. So they're very similar when I was reading about them. They're like very similar to what event charts are, especially like semantically, you have to deal with what it means when events, how events are occurring in time, the whole timing, and what
mm.
signals part of that is sort of very relevant to the semantics at least. So that's sort of part of the reason I'm investigating these languages is because I think anyone who's creating like a reactive notation or formalism should understand what these were doing because they were tackling pretty much the same problems. Maybe a little different in terms of the context was more real-time systems as opposed to like web applications, but I think there's like a lot of work being done, a lot of groundwork that is worth knowing about.
Yeah, totally agree. I think a lot of my interest in these foundational languages for this particular programming paradigm stems from similar inspiration and interest. So yeah, I think that sort of helps why this we're starting with this particular paper. Um,
Yeah.
and I maybe the first thing this paper touches on, and it's probably worth us really fleshing out this idea of what is a reactive system, what are the characteristics of reactive systems, um, and
Totally.
where if you understand that, then you can understand when you'd want to use a language like ESTEREL or it's funny, I've never said it out. Lustre.
I think it's LUSTRE.
LUSTRE. Oh my god. Okay, LUSTRE and Signal. Like
Yeah.
when would you want to use these particular languages? And I think it all comes back to what is a reactive system. Um, and there's a paper that I'm surprised wasn't referenced in this particular paper called On Reactive Systems by Harrell. It came out in 1985, and it sort of described the dichotomy between what a reactive system is and what a transformational system is. And that's what
Yeah.
this is building on. Although I think the characteristics that they define here are much more helpful in understanding what it actually means. But I was surprised that it wasn't referenced. And maybe at some point we'll talk through that paper as well. Um,
I think the sterile references that, I believe.
mm,
So, and this references that. So I think it's just because it's like that. It's like a derivative
yeah.
definition around reactive systems. Like most of them either directly reference
For sure,
Ralph's
for sure.
paper or they're referencing something that references it. So it's definitely like an influence, even though maybe they haven't explicitly pulled that one out. Um, yeah, I think it's definitely still there. Um,
Yeah, but
and yeah, definitely.
the definition they used in that original paper is sort of summarized as oops, lost you there for a sec. It sort of summarized as described here is a reactive system is a system that continuously interacts with its environment. Um, so it's not just outputting a
Yeah,
result, and that's sort of the definition of a transformation. It's just like transforming an input into an output. Like that's very different than
yeah.
what characterizes a reactive system. Um, there's talk of like what of real time system, and I think that's something that we could touch on later. I think other parts of this paper sort of talk about the nuances between like a hard real time and soft real time system.
Yeah.
But I also didn't know if that's something you wanted to focus on now. Like how important is this
Well,
concept
I
of
mean,
real
I think it is
time?
context for this because if you think about programming in the 80s, what they were programming,
Mm,
uh, what reactivity meant and what things you were programming with reactivity are different.
yeah.
Like I think GUI programming, it was more 90s, right?
Yeah. Like the
It,
web was coming in that time.
so this, what we're trying to sort of apply reactive principles to web programming and I think more just generally GUI programming, but they didn't really have that then. And so when they're talking about reactive systems, they are talking about real-time systems. And
Hmm.
so the environment there is actually like kind of outside of the software.
Yeah.
The environment is either hardware or what the hardware is interfacing with, depending on how you define it. I think they're more actually referring to like the external world, and typically the reactive system will have like a hardware part, which is like say like a sensor, and that's interfacing, taking the signals from the outside world, and then there's like a reactive software part that is handling those signals, and then output is typically
Mm,
like some sort of hardware output.
yeah. Yeah. It's very different than like what we think about today, where it's like
And so I think,
we don't care about
yeah.
hardware anymore. Really, like that's it feels that is very extracted away from you unless you're doing some very like low level embedded software. Um,
And it actually does make this whole reactive system question very complicated, at least from my point of view. I don't really
mm,
know how to find the terms they're referring to, such as the environment. Like in a web application, what is the environment? Is it just like, our users typing stuff sometimes, but there's also sort of like other software systems could be considered part of the environment
mm-hmm.
in that case. Um, and yeah, so you're not really, we're not dealing with hardware at all. We just get, so maybe keyboard events is like the closest we get.
Yep. Yep.
And so it's a whole different ball game in some respects. So I think that's important context, but I'm not really sure how to deal with it. And I think there's still a lot of things to learn from this. But
Yeah.
yeah, it is something like at a higher level, I do struggle with, and I do wonder whether reactive programming for real-time systems is actually a different thing. Maybe, maybe not. Like it will become clear, but they really focus on viability and what guarantees can you have about what the program will do.
Mm-hmm.
And that's obviously a nice to have wherever you program, but is that something web apps need to have? I think we pretty much program as if we don't need that, at least
Right.
generally.
Like if you
Um,
can't if you
yeah.
can't submit your form because there's a robustness issue, like you could refresh and maybe that will fix it, as opposed to if we're talking about a
Yeah.
reactive system being an airplane, um, or street light or a power plant. Like there's a certain level of importance, and it's well, I think what's interesting is the examples that are sort of listed right in the first paragraph are sort of like infrastructure level software that's being run, right? um
Yeah.
and it's very different. It has very different characteristics than like the very like productized software that most people are creating nowadays, whether that's for the web or a mobile app or a desktop app. um, like
Yeah. And we've sort of spoken about like state charts. They this sort of got hijacked a bit by like the telecom stuff, especially
mm,
the UML,
yep.
SCXML's notation and all the semantics. And state charts is all about that real time systems, the origin of it, like with Terrell's avionics. And we've also spoken about how whenever people use examples of this stuff, it always seems to be like a hardware example, like oh a microwave or
Yep.
this. Very natural for doing that. When you actually start to build software systems with it, it becomes a difficult and there's like complexity there that seems to not either the notation doesn't deal with or it's just harder to reason about because it's more abstract stuff like
It's
that.
harder to reason about what your
Um,
environment is. You're creating a software system. What's your environment?
yeah,
And there's so
yeah, and
that
what are the
boundary is more
boundaries?
fuzzy when it's just in software land, as opposed to I'm
Exactly.
making a watch and there's gonna be four buttons on this watch and that's the
Yeah,
environment.
yeah,
It's
and I
very
can't
different.
change that, and I can't change where the event like with, with some of the stuff you've been doing. Like it's really difficult. Like where do you put the logic to handle an event, or where when does an event like a keyboard button get mapped to something that
Yeah.
has a more semantic meaning? Where and when is that happening? At all, and that changes how you model it. Like is the state chart or whatever model, is it dealing with the semantic mapping? Does it know about it? Or is that happening in the template? And so this lack of a clear boundary really means there's more modeling options, which means it's harder to choose what to
Mm-hmm.
do, essentially. But I think it's partly like a choice thing, and then partly I would, my hunch is that the actual, at least the semantics, possibly the notation, is easier or is models these sort of systems, real-time systems,
Mm-hmm.
better than it models like, I don't know, what GUI systems. That's my hunch.
Yeah.
I'm not sure about that because it feels, and this is, I guess, a tangent, but I think it's like it's all the motivation for learning about this stuff is sort of like where it also doesn't apply. But um, yeah, the GUI. Whenever you start programming GUI, the state charts feel like they're going to be perfect, and then when you write them, it feels like that it's a little off. That's my sense about it.
Yep. No,
Like
I,
I
I,
think this is better. This is better than what I was doing before, but it still isn't quite what I'd hoped. Like I'm still not really sure what this whole thing is doing. It's just at least it's in one place, and at least I can kind of see what events are coming in, and it's kind of organized by state. But I don't really know if this event gets into the state chart, how it all comes together. I have to really like debug that every time.
yep.
Um, yeah, I
Yeah.
don't know if you've on that.
No, I have similar experiences. It's helpful for thinking, but sometimes it isn't how I wanted to execute and sometimes, as we've talked about your motivation behind event charts, like um, sometimes there's still behavior that's lost as we sort of uh, com- I'm gonna use component, and it doesn't, it just
Yeah,
some
yeah,
abstract reusable thing, right? Like when you
yeah,
start componentizing things, and things get lost, and that's one of the things they talk about, like um, in this first thing about concurrency. Um, and maybe we could touch on it, because so we talked a little bit about reliability being like a super super important, reliability and robustness being really important characteristics of a reactive system. Concurrency is the first thing they bring up in this paper, and one
yeah,
it's probably worth talking. Concurrency has like so many different meanings these days. It's really hard to know exactly what they meant back then. Um, but the reason I was brought up concurrency is the first, the second sentence they talk about here is usually a reactive system is complex enough where you need to break it into different concurrent components that are cooperating
yeah,
together, um, usually by event messaging. And
yeah,
and so yeah, like once that starts happening and you start decomposing a system into these components that are talking together, like there's still that behavior that gets lost. And yeah,
yeah,
I don't know. I don't have a solution for it, but I
yeah. I mean,
definitely
so
sympathize with that.
concurrency, yeah, yeah, so yeah, totally. I think it's like a general, it's a general context for a lot of the work we're doing. I think it's like state charts are good, but not. I think it's like nearly there is what I'd say, and they might also be a piece of the puzzle.
Yeah.
I think probably are or something similar. Um, yeah, and so yeah, coming back to the paper, so I think reactive systems. I think Harrell's paper makes it pretty clear, and in the context of the 80s again, it's sort of like, well, most of the software was sort of calculation based. Inputs run a function or series of functions, and you get an output. And then there's these type programs come along where they're sort of running continuously, and they do different things depending on what has happened before. And ESTEREL was sort of looking for a term for what that is, and it was also looking for tools to be able to program those things. And so chart, and then the term like reactive systems.
Mm.
And I think in some sense, I think that's the most important part. And then I feel like some of the qualifiers they give for that is sort of a way for them to justify why there needs to be a new term. But those like environment and hardware and stuff are maybe not the essential elements. Um, and maybe describe a more specific type of reactive system. That maybe be one way to look at it.
Yeah.
Because I still think like web apps is still very like much that, but they don't are quite the same. So there's like a broader category and then maybe subcategories of reactive systems, something like that. I think that's like essentially what is important about that and about reactive systems. And then concurrency. Now I can't quite remember how this paper goes into it, but um, very much in the notes and very much in all of the writing around the synchronous languages, concurrency is pretty much only for ease of notation, and it's not hardware level. It's not like actually executing in parallel. They get compiled into synchronous code, and
Yep.
it's basically for conciseness for ease of modeling. Um, but it's not, yeah, it's not like things are actually running separately,
Yep.
and that's part of like the synchronous. Synchronous programming is really about having concurrency in a deterministic way. So previously there was like concurrency, they always something like Ada, but it's asynchronous, and that means that it's not deterministic. And so synchronous languages are really about solving the problem of when we have a concurrent notation that is deterministic, and
Yep.
the determinism is important for these people because they want to program real-time systems.
You're heading on the next
Um,
characteristic of reactive systems where you want to
yeah,
have a high or uh, optimally like extreme like maximal deterministic system where you know everything that's happening and it's going to happen again the same way given the same inputs. And it's sort of interesting that uh, determinism sort of has like this like functional kind of framing of it. It's like given the same inputs, you have the same outputs, which I
yeah,
find interesting. Even though reactive systems are defined in the context of they're not something that is transformational, there still is this concept of there's inputs and outputs. Um,
yeah, and I think that is an interesting point that there's probably some things that are almost in between, like maybe some command line style programming where you can set some flags and run stuff is maybe in between.
mm,
Um, what I think I've seen somewhere where system is defined as where the main part of it is a reactive program, and a reactive program is defined in a certain way, but I'm not really sure how useful that definition is. Like if you have a really big software system, I think it's just a non-trivial amount of interaction, continuous interaction, rather than being like the majority of a program.
yeah.
But then there's also like the question of whether you should, if you're writing an application and it has some reactivity and maybe some transformational elements, you should really be able to choose the tool for the job and have the reactive part programmed with something that is good for program reactivity and the transformational part programmed in something that is good for that. Um, and I think deciding what is the reactive system the one that sort of owns the transformational part, or is there some sort of higher coordinator? Is interesting as well. Um, there's just a couple of I've got some quotes that are not from this paper, but coming back to that sort of currency part, I think they really capture what's going on in the context. Is so that
Mm,
sterile semantics has this section which is the quote is quite amazingly all the available techniques force the user to choose between determinism and concurrency because they base concurrency on asynchronous implementation models. where processes non-deterministically compete for resources. This leads to the problems that are really unnatural when programming reactive systems and when reasoning about such programs.
Mm.
And then, so that's sort of like at the time they're writing these languages, you can't have both.
Yep.
And then in terms of like the actual way that this happens, the Argos, um, Argos, I think it's the original Argos paper. It's called Argos in automaton-based synchronous language.
Mm-hmm.
Um, it says that the synchronous languages are intended to be compiled into centralized sequential code. Parallel composition and the communication mechanism are introduced only for description purposes at the level of language. They compiled into something sequential, so they do not imply explicit parallelism and communication at execution time.
Mm.
I think that's important to sort of know about these. And yeah, I think it's interesting context. Also applies to state charts, all of that.
Yep.
I'd say.
Orthogonal states and state charts, it's the same thing. It's this like facade that you have
Yeah.
these things running at the same time or concurrently or whatever. But it's really just a helpful notation to decompose a state space to avoid, state explosion, right? So it's a more concise way. It's like using concurrency to more concisely describe the behavior of a reactive system as opposed to true
Yeah.
concurrency, because that's not actually how the semantics work. It's still one
No.
process. It's executing the state chart. They're not running concurrently. Um,
No.
which is a big area of confusion, I think.
Yeah. And most of the state chart is extends finite state machines or like adding concise notations to it.
Yeah.
And pretty much apart from I think extended state, you ignore extended state, you could compile every um, state chart into a finite state machine fairly easily. Easily in terms of it's easy to reason about how you do that, but it's unwieldy.
Yeah.
The extended state is the finite where because finite state machines have finite states, and extended state is sort of like infinite. It's a little different, but
Yeah. So one of the things I think interesting that comes along with reactive systems is the concept of events. And I'm sort of surprised that it wasn't sort of a talking point in of defining what a reactive system is, because
uh,
I feel like that's a core part of the paradigm of synchronous programming is this concept of events, and I
yeah,
think that this paper talks about it a little later on. I have some highlights here that you were touching on earlier around
yeah,
CSP, like communicating sequential processes, and ADA, where there's point-to-point communication. My understanding is just like you have a reference to something and you're sending an event just to that.
yeah.
Is that your? Did you take away? That was one of the very small questions that I wasn't 100% certain on, but that's how I interpreted it.
Sorry about the ADA part or about events in reactive systems.
Point-to-point communication. What it's talking about, in my head, like CSP, there's all these different processes running, and they probably have references to each other. And so if I am process A and I want to talk to process B, I'm gonna figure out where that channel to get to send something to process B, and just send it to
Yeah,
that.
yeah, yeah. That's how I understand
Okay,
it.
okay, cool. Um,
And I definitely think like CSP is something we should look into as well at some
yeah.
point. But I think the main part, like the main point, is the unspecified time
Mm-hmm.
is like asynchronous, and that is doesn't have deterministic properties. Um, Interestingly, another bit of sidetrack, but the actor model is also asynchronous.
Mm-hmm. Yeah.
So it's interesting that you would choose to pair state charts with actor model.
Yes.
That makes sense at some level, but it is worth like so you could think of having like the state chart, if you had a fairly large state chart, within that it's deterministic, and then at some point you want different processes, and then you could have an actor per process. But multiple actors per process destroys determinism within the process. You'd only get determinism in each little actor. So that's sort of one negative about continuing to break actors smaller and smaller. And something like JavaScript, it kind of doesn't matter because JavaScript is single threaded. In the way it works, you can just about preserve, like, but it's not guaranteed at the notation level, depending on how the actors are implemented.
Yeah.
It's sort of like a weird thing. Like in XState, you can break a state machine into actors with parallel components, and it will basically behave the same as if you were in one state chart and using concurrent regions,
But
pretty much.
if once you move that to another thread or maybe another
Oh yeah,
tab or server, then
exactly.
that there's potentially some unintended consequences of doing that, that you have to be
Yeah, like
very
I think I
careful
said
of.
before, if you took every XState system and then actually added some random delays into the event communication, I think some of them would break.
Hmm. Yep.
If you simulated asynchronous or actually made them really asynchronous, I think there would be some like relying on event order. Um, so coming back to events, I'm pretty sure again it's just because this is sort of a summary. It's sort of taking it as given our reactive systems because I have seen them more focused on um, in other in like the
Yeah.
actual ESTEREL papers, for example. But events are very I sort of call for the definition of synchrony, which is
Hmm.
like the core concept of synchronous languages, which I think is like the next section.
Yeah.
You've
Right
got it
here.
highlighted there, which is I think is quite a good way of defining like synchrony. And again, synchrony, like there's the synchrony hypothesis, which is essentially what they're referring to here, and then there's like evolved different definitions of it and different levels of like strictly like synchronous or can't remember the exact terms, but like there's a loose type of it. It gets a little complicated there, but I think in this form is it's quite a good like paragraph describing what synchrony is.
Yep. And it's important to to reiterate the core tenet of these synchronous programming languages is known as the synchronous synchrony hypothesis. Um,
Yeah,
and it it sort of takes a little while to wrap your head around it, because it's sort of like this, like, oh, in an ideal world, if we have these guarantees, then we can ignore time, and everything will be deterministic and work. Like it's this really, I don't know if you feel
yeah,
the same way about it, but it's like this very, like, it's this very idealized state of the world, but also like holds true when things hit the ground and actually are like running and executing on a computer. Um,
yeah. I think it can depend a little on maybe the type of programming you're used to. I think if you're mostly doing, say, JavaScript stuff, you're pretty used to just doing things in order and the same thing happens every time.
yep.
And so maybe it seems like almost a moot point. Like, why do you even need to say that?
Mm,
But then if you've been doing true concurrent or true parallel programming, then it's like not clear at all how you would achieve that potentially. And that's sort of why it's sort of in between. It's not really true not processes in parallel. It's just a notation. That's sort of the key to it. But I'd say synchrony it's almost such a simple idea that you think it can't be that simple. Just the idea of it.
yep. Yeah,
Put the
that.
same things in, you get the same things out in the same order. But the key, and again, the context of it around sort of dealing with real-time systems and everything. I think the key is that it's like a logical timing. So
Mm,
it's this idea that you're not going to worry about how many seconds these things take. We're just going to assume it's going to be quick enough. And the main thing is that what they do is happening in the same order. So they process the first event in time to get to the second event, essentially.
Yep.
But it's really about if event A and event B and event C happen, then you always get X, Y, Z as the output.
Yep.
That's and so that's when it says like it's matching the indices in the output to the input sequence.
Yeah.
But it doesn't really matter if processing event A took 10 milliseconds or 20 or 30, as long as it happened within some sort of frame.
And one of the core assumptions here is you only process one event at a time.
Hmm.
I think that's really important. I'm pretty sure all three languages follow that assumption,
Pretty
although I'm not
sure.
100% certain. Um,
And I'm pretty sure like the extensions of synchrony refer to how like have you actually processed the first event before you get the second event? Like,
mhm.
or is there some buffering going on? Because you can imagine you could take a year to process an event, but as long as you've queued up all the ones that have happened in between time, and you can still preserve the order of things. But
Mm,
I think the original notion of it is it's happening like quite quickly because they're real time systems and it's
yep.
doing the things in a quick amount of time. But there's sort of been extensions to that, like the big steps paper goes into that a lot more.
Yep.
Like what is a step and how does that are you buffering? Is it flowing very much in real time?
Yeah. And
Um,
I think following that, like we sort of remove if we like I think the synchrony hypothesis removes time from the equation, um, which is
yeah,
interesting. But that doesn't mean time isn't important in these systems, right? Like maybe there's a requirement
no,
that's like after 15 seconds turn off the screen or do whatever, right? And the way that works as described in this last paragraph is time becomes is an external event from the system. So something is sending these timed events in, and we can do something with them. And as long as again the order of those events is the same, then we'll get the same outputs.
yeah,
That's
100%.
that's how we sort of like say like, hey, time isn't important, but it still is, or semantically it's not important, but like we can still have it as this like concept in these systems. Um, I don't know. Yeah, there's something interesting there about like that. If something was finagled, it feels like for that to be happen, but it makes sense too.
Yeah, yeah. I think that's about right. I think the next part is interesting because it talks about how like you can have simultaneous events.
Mm. Yeah. What did you make of this section? I was. I think it confused me a little bit because my just the conception of events in my head probably very skewed towards state charts, uh, and like what it meant.
Yeah, I did find it. I didn't find that diagram look the clearest. I think it sort of refers to like the event being seen by every module at the
Mm.
same time. Kind of what it's getting at. Was there a part? Maybe it's not in this because we have the notes. There's like a
Yes.
tutorial notes, but in there they actually touch on the broadcast aspect. Um, so I've got it up uh, here.
What page?
It's on the second page of it.
Second page.
It's synchronous programming is the heading, and there's a bit about the synchronous broadcast at the bottom of it, and it's just referring to how sort of like how the synchronous concurrency is enabled.
Yeah, right here.
I just thought it's interesting that this whole part of it is sort of like the secret sauce in some ways of all the synchronous languages, it seems to be. But it's also like where the semantic complexity lies. Also, is like an event happens and then concurrent regions can do something, and that thing can be seen in the same step.
Mm.
So it's sort of like the outputs can actually influence the process. Outputs of each region can influence the decisions being made in that reaction,
Yeah.
and like the feedback into the reaction via the broadcast. And I think it's something really interesting to explore. Maybe again into some of these other papers, but so the what's being referenced there is the ESTEREL paper, or at least yeah, ESTEREL, and then one of the authors of ESTEREL has got his own papers talking about synchronous broadcast.
Mm.
Um, and also, what's interesting is ESTEREL, I think, had a semantic for synchronous broadcasting when state chart did it. That was how it worked, but I can't remember if the semantics were really laid out originally in that first paper.
In which paper? The sterile paper?
Just
Paper?
the for visual formalism papers. I don't know if Pharrell says event broadcasting is the mechanism,
He never goes into it
or
though.
like, but he says, oh, you could also use other ones perhaps, but he never goes into it. Whereas a sterile paper is that same
it
time,
it
but it actually has a
it's
semantic.
like one of those. It's like one of those like math petitions that's like I'll leave the proof up to the reader. Right? It's like,
Yeah,
oh, I know this is true, but I'll let you prove it. And then it's like some of those like Fermat's last theorem proof. It's like I proved this in 3 steps, and then it's been like hundreds of years, and we just proved it through like extremely complex like mathematics. It's sort of like that. I felt like.
totally, totally. I'd love to find just an image, which I think I can bring up pretty quickly, of the broadcast in a sterile. I can't remember again. I can't remember this paper actually as goes into this, but broadcast is so confusing, which is interesting because it's sort of oh yeah, here we go.
Let me figure
Presented
out
as this
how.
foundational. I it's signal
Pause.
broadcasting, so it's
Emit A. So present here is
yeah,
like wait for B to happen.
yeah.
Um. So don't do anything. Wait. What would pause mean? Would it
It's
like wait a
just
tick?
skip a as yeah, yeah.
Okay. Skip a tick. Emit A. Wait for B. When B happens, emit C. Then wait a tick and then emit A. And then I'm assuming this means a current process,
Yeah.
which is pause, wait for A, then emit B.
So what's happening is if you ignore the pauses because they both pause on the first tick,
Yeah.
the first region is saying A exists. The second region in the same cycle or tick sees that A is present and then emits B, and then on the next cycle, the first region then says B is present. But the key
Mm.
is like the A is emitted in the same tick that the second region is looking for it.
So this emits B in the same tick as this right here,
Yeah,
and then the next tick this says, "Hey, there B's
yeah.
here." Okay.
And I think the paper maybe touches on that, but there are some, the Esterol has like some deadlocks. You could write it in ways that have sort of deadlock if you weren't careful, but it has sort of automatic um, will reject those programs. Like if one is waiting for A and then it'll emit B, and the other one's emitting
Mm.
waiting for B and then will emit A, you can end up in those scenarios. I just think like just in general this idea that things are going back and forth between the parallel regions in the same cycle.
Yeah.
It it actually is really a source of complexity, but it's also like what the whole point of these languages in some respects. So that's an interesting
There's a
duality,
tension there.
or
There's a tension there.
yeah, tension. Tension's a good word.
It,
Yeah.
because it be, and this is what
Um.
we are talking about, that behavior, some of that behavior becoming invisible.
mm,
It doesn't feel immediately obvious like what's actually happening, even though it is deterministic, right?
Yeah. Yeah. Yeah.
Which is an interesting point because I feel like determinism is usually like this determinism. I feel like determinism is like sometimes like framed as like a silver bullet.
Yeah. I would say it's great if the same thing is always going to happen, but is it much use if you don't know what that is going to be?
Until it
So
happens.
determinism, yeah, exactly. Determinism and like understandability are not the same thing.
Yeah, yeah.
It's sort of like Harel's watch. If you go into that Citizens Watch example and actually try and understand what is going on, it's so confusing. You have
Mm-hmm.
to basically resort to simulating and then seeing what happens, and then you sort of can map back into the behavior. Um, but and actually, part of the verification methods on these programs are to run them, which is an interesting point.
Wait, sorry, say that. I finicking with the window. Can you say that again?
Like some of the verification techniques, one of them is sort of, I think it's like exhaustively running the program with input and then defining a fail condition.
Mm.
And then if it doesn't fail, it's pass the test. And that's one of the formal verification methods. So actually simulating is valid
Yeah.
as in a way of seeing how something works, but I think it's not ideal. Um, but anyway, I think that's probably enough of like a overview of the high level stuff. Do you want to have a look at like each language like quickly?
Yeah, should we talk about the dichotomy?
And
Right here.
two classes, right?
Also, maybe another high level. So we've been alluding to this, but there's like actual dichotomy talked about in both papers. The difference between a reactive system and an interactive system. Um,
Yeah,
is that something that you? It's sort of high level, so it might be helpful to talk about before we dive into like each particular language. Um, those are the only two things that come to mind, like maybe worth touching on briefly before we dive into each language. I think the
yeah,
notes. Let me hop over to the notes. The notes talk have a summary right here on the first page, sort of about the difference between like an interactive system and a reactive system.
yeah. I wasn't impressed with how these are defined, and I've seen the um differentiation between these elsewhere, maybe the sterols notes.
Yeah,
It seems like not they don't seem like exclusive. So if you have like say transformational, reactive, and interactive, they do not seem to be exclusive categories, but not even like it feels like interactive system is a term they sort of realized they need to differentiate
yeah,
with like say an operating system. That's the examples like an operating system isn't really a reactive system, so it's different, but it's kind of similar.
Yeah, I think like
Ah,
one of the points they're talking about is like, an operating system scheduling different processes and threads and whatever is like non-deterministic. Like it's not important that it's deterministic. I think that's like one differentiation.
yeah, and then
Um,
others like they talk about the real time element right there, which is
yeah,
have to react to an environment which cannot wait, and so like a physical process. And that's where we were talking about reactive system then versus reactive system now. Maybe we're about some interactive systems.
yeah,
Um, so I don't really know what to make of it. I just think I wasn't really happy with how they've defined it. Mm,
yeah. The thing that one of the differentiations I was thinking about is sort of like, and there it's not a firm boundary, but it's sort of like how many events are you processing at once, right? Like I think a big
yeah.
difference between an airplane and a user interface is like a user is not spamming events that are being inputted into this reactive system. Maybe they'll
Mm,
click on something every second at most, but like there's a very different level of events happening both on the input and the output,
mm,
as opposed to a plane where if you're flying, you have, I don't even know how many sensors streaming information into a central computer. You have pilots controls. Like there's almost like a bombardment of events happening, and it's really important that you could like deterministically figure out what to do as like you're just being bombarded with all these, continuously bombarded with all these events. Maybe sometimes like there's a
mm,
gap, but like I that was like a really fuzzy difference that I was thinking about between these two things.
mm. Yeah, but I'm just not even sure. Like, I'm not even convinced about the categories that they've
Mm,
chosen. So, yeah, I didn't go too deep into thinking about
yeah,
categories.
I agree though. I think there's high overlap between them, and
Yeah.
maybe like some things can get away without being deterministic, but that doesn't mean this paradigm or these languages or in notations aren't useful for them. I wouldn't go as far to say that.
So I think, I mean, determinism. If you don't have determinism, it's what's the word? It's sort of like a requirement, but not sufficient for an understandable
Mm, yeah,
precondition,
it's a precondition.
maybe as well. Like, if you don't have determinism and you want to look through and see, oh, what is this program going to do? It's so hard. But just having determinism doesn't mean you can really understand it very easily.
Yeah.
At least understand without simulating. Um, like, here's a state chart. Do you understand it? If the state chart was non-deterministic, it'd be harder. But just the state chart isn't necessarily going to be really easy to understand.
Yeah.
Um, yeah, on the point, the imperative point,
Yeah,
that was the other one, right?
let me get that up. Yeah, and you know what's funny? So for the person listening, what the distinction they're making here is that out of these 3 4 languages, um, there's sort of can be categorized in 2 different ways. We have synchronous programming languages that are imperative, so you're sort of writing similar code to like you would in any general purpose programming language. So there's for loops and if statements and um, uh, built-in parts of the language are around waiting and for events and then emitting events or outputs. Um, and they're sort of good at certain things. They're talking about user interfaces here. Um, for as one example, and also some lineage of state charts being categorized into this formalism, which I found interesting. And then there's data flow
Yeah.
languages, which was sort of funny because they're sort of have this very transformational system kind of vibe to them because they're sort of just transforming transforming like data and in this very spreadsheet kind of manner. Um, and it's
It's
no
transformational is sort of like a higher order, like in this context, because time is an input. That's the thing, right?
yeah
It's
okay
like
that's a
higher
good
order
point.
transformational, and so like part of it is dealing with time is so complicated. If we can just externalize it and then act as if we're transforming things every step, it's sort of like that whole functional trick of just making something an input, right?
Yep.
And then you can have pure function that runs, and
Yeah.
then you can understand the function.
Yeah, when when you put it like that, that's where like the whole paradigm of asynchronous programming, so like observables and streams, like um, I feel like also comes into play as well as FRP and all those lineages stem from I think these latter like the data flow languages, which is interesting, right?
Yes, and that's a good point because I've often when people talk about reactivity, they're often talking about sort of like signal based synchronous programming.
Not to be confused with the signal programming language.
Well, I mean, it's kind of it's called signal because it uses signals, so it's sort of the same idea. But yeah, totally. Um, but it's in some ways it feels quite different when you're dealing with signals as opposed to events. But there's an equivalence, and people have done signal-based state charts. Um,
Mm,
but yeah, it is like if you like solid, right, with signals, it's trying to relate some of this stuff to solid when you're looking at state charts, and sterile is a little tricky, but then you see these other data flow ones which are in the same family, and then
yeah.
it's a lot similar to what they're doing. Yeah, there's like a general equivalence, I think, across a lot of the notations, and well, especially because these all basically compile to finite state machines, right? So
Yep.
it's the notation that is really the important thing because they turn into essentially the same stuff.
Mm-hmm.
Um, so yeah, it's like so it's interesting that a notation is better suited for signal processing, and that's what the Lustman signal are. And it also makes me wonder whether a big application would need bits of both styles.
Yeah.
And it's that composition again is a question. If you're using little languages for those parts as opposed to just trying to do it in one general language.
Yeah. I love the I so the thing I like when we talk about like present day signals, at least in context of the web, the thing you get for free with them is derivation, right? Like you could define these relationships between different pieces of data and the underlying runtime will just figure out when it needs to derive things as efficiently as possible, right? And I think uh, like signal, the signal programming language that we're talking about here, for example, does something very similar. Um,
Yeah.
I love that aspect of it. When you get to like ESTEREL, particularly state charts and part of the lineage like Argos and the combination between the two, which is called sync charts. Um,
Yeah.
what I love about those notations is selective message passing, and what I mean by that is like depending on the state we're in, we're going to selectively accept these events and we will just ignore everything else. There's something that's what you get
Mm.
for free with those. That's why I don't like the I think they used the wrong word here for like imperative language. I don't think that quite hits it. I think that's very focused on specifically on a sterile rather than what a sterile and state charts and the combination between the two of those things is trying to get at. Um, I don't
Yeah.
know if you would disagree with that. I don't have a word that
Yeah,
describes it though, but I think it comes back to this like concept of selective message passing.
Yeah, I this like two classes of languages. I didn't really, if you actually look at the notations, I didn't really understand. I mean, ESTEREL, I know ESTEREL bit of like I've just looked into it more, and you can
Yeah.
declare variables. Maybe that's the imperative part of it, but and I guess essentially like Lustre and Signal are a bit more focused on. I think they're related or in a similar class to some of these circuit design languages.
Mm-hmm.
Like, is it VHDL? One of the, where you're,
Yeah,
it's
I
like a
think.
DSL of little language for um finding like circuit
Mm-hmm.
for circuit design. I think there's some relation because he talks about block diagrams, and they're definitely a bit more focused than a sterile. A sterile has more of like your general programming affordances in a specific notation. It's constrained.
Yeah.
I think maybe that's what they're trying to get at. But I like if you look at all three notations, I didn't think like that distinction was really worth making in the way they've done it. But
Yeah, I agree.
also the imperative in general imperative is like yeah, it's just a
But
hand wavy word.
yeah, it might be helpful. So, do you want to dive into start with the sterile?
Yeah, totally.
I think this paper had the same examples, just better formatted. Let me find those
Yeah.
right here. So
Yeah. Okay. Yeah. Yeah.
these are two sterile programs, and I think it's helpful to sort of
Yeah.
just walk through them. Um, so first
Yeah.
off, first thing you see, like these are a module in a sterile, and so the whole point
Yeah.
is you. This is a sub component of the entire reactive system, and you can compose these together. And the boundary of composition is input events and output events. So on the
Yeah.
left, on my left, there's a module for defining a speedometer, which is basically taking in time and meters and outputting your speed. So it's a converting these these input events, like how many times have the wheel spun around, how many meters have the wheel spun around, and how many seconds have passed, into what's your speed. Um, uh, yeah, and so you can create a loop that and define variables like distance, and then as time ticks on, you can add meters to every time there's a meter, we increment our distance and wait a second, and then emit uh, speed times distance. I think that's what it's doing. But anything that you want to add there?
Yeah. So essentially, every meter, every meter event or signal firing, it increments a distance variable, and then when it gets, uh, it does that until it gets a second signal or
Mm-hmm.
event, and then upon that, it emits the speed output signal as which is sets the distance. You can think of that as like raising an event or sending an event somewhere. But because it's sort of like it's more signal based in a sterile than maybe it just, but they're essentially equivalent.
Yep.
Um, yeah, every meter the distance increases, and then when you get up to a second, then you output the distance, and then it resets, so it goes into that loop again. Um, and there's actually really it's quite simple to convert that to a state chart.
Yep.
I did a couple of them, but like for this one, you just have one state
Mm-hmm.
counting, and then you have two event handlers, one for meter, one for second. And if you get a meter event, you increment the distance, and if you get a second event, you emit the distance, and then you reset the distance.
Yep. Yeah. What's funny is this example actually, as I was talking about, there's no selective message passing. You just it's simple enough where you just always accept the events because there's a single state, right? Um, but I could see how scaling these modules out creates that complexity that doesn't where you those bugs probably start coming into play that we typically see with like uh, what's canonically called the action event action paradigm, where we're just running code directly in event handlers, and then there's increasing amounts of handling about like, oh, we're in this. You sort of need to recreate that state, that finite state machine to figure out what you need to do. um, that's like the question I
Yeah,
have. How does ESTEREL handle that? um, and I feel like it sort of ends up being similar to like imperative, just putting imperative code directly in event handlers. That's like my guess.
yeah.
I don't
It's
know if you disagree with that.
no, I think so. I think so. It's like that. It's still got the concurrent parts and the synchronous part, but it
Yeah.
doesn't have the event first part
Yep.
necessarily.
Yeah. And so at least with this, at
Well,
least with the sterile, you have determinism. So the same thing will always happen, but like I can imagine those behavioral bugs creep in just based on like some of the examples that I've seen of it.
yeah. And this is a very brief look at the syntax, and the sterile papers go into a lot more depth.
Yeah.
I remember seeing, so they have something sort of equivalent to activities where you can
Mm.
just run things on their own. But they're a little different state charts because they're not as isolated. They can still receive like global signals and access the shared variables.
Mm.
Um, whereas in state charts, they're isolated by events. At
Yeah.
least, well, I don't know if that's like the original formalism specifies that, but I think most of the implementations have gone
Yeah.
down that
Yeah.
road because it gets very tricky having a shared variable. Um, I'm not even sure if it's sterile. It probably has ways to. Yeah, the problem is if
Detect
you have
those race
multiple
conditions.
activities, maybe, or I mean, it's just going to be if you have multiple. I guess state charts do have this problem. Like if you have multiple parallel regions, they can both write the same context in the same depth.
Yeah. Harel talks about that in one of his papers about that like those race conditions and how the semantics help alleviate that. I think, but it's I think it's an open
Yeah,
ended question in both languages.
yeah. Another sidetrack, but I've observed that most of the time it doesn't matter because mostly you don't have multiple parallel regions writing to the same variable,
Yeah.
which is kind of weird. It's not like a priori obvious that that would be the case. And it's sort of this idea that multiple places want to read from it, but only one place is generally writing to it.
But that's
Um,
like because you're sort of like conceptually in my head, I want this one thing that is orchestrating that piece of data that others might want to read from. Like that's sort of
yes,
what it feels like. That's how the decomposition of the behavior happens. Um,
yes. Although there's so many dimensions which you can sort of cluster on in a state chart,
yeah.
it's kind of interesting that it's almost always true. Always, my experience is always true that if you're grouping events into a state, you're not necessarily thinking about the assignments at that point,
Mm,
but there's some correlation between maybe what your events are getting, which makes sense because they sort of have a semantic,
yeah.
meaning. But and there's not even I can't think of many exceptions where all 9 out of your 10 states are happy, and then one over here is like randomly writing. It very rarely happens. But as you say, it
Mm,
could just be because of how you structure it. But it's kind of interesting. It makes me wonder if there could be some sort of like constraint based. What I see with these notations, like state charts and event charts, is these things that you think about in your head. Finite states are like, well, with these booleans, what I'm really trying to say is this is in a configuration where events are handled in a certain way. And so finite states, state charts and finite state machines say, okay, we'll make that part of the notation as explicit. And then event charts, what I see that as well, I want this event to be sent here so that this processing can be happen, and then these events are emitted, and then this processing happens
Mm.
and goes here.
Yeah.
And that's something that you sort of have to think about implicitly and manage in your head when you're using state charts or anywhere else. But if you make that explicit and have something that actually shows you that, um, then that would be like really, really helpful. Then with the sort of like writing to extend the state, I made me think, well, if this is true, maybe you could actually have some sort of explicit notation that is like region-based store or state that you can declare what can write to it, um,
Mm.
so that is sort of like constrained and explicit that okay, region this person has the rights to the right to these areas of state. Because I've noticed that people seem to have this idea that they want local state. For example, people with state charts and X state have asked for scoped state to substates of a machine, and I've always thought it's a little odd. And I think part of it is just knowing what is going to write to this part of state. You just want to know. It helps you think about it. But if you could just say, well, it's only this part, but it's still like global, it's still shared.
Yeah.
That's an interesting word I've had, but a pretty off piece
Mm.
for this paper.
And then something else implicit will come up, and you're like, I want to make that explicit too.
Yeah, and I think the thing is you can't have the same notation making everything explicit. Could you make it explicit somewhere and then have some orchestration or composition?
Hmm.
Then you run into linking costs, which is you've sort of referenced the same entity in different forms all over the place, and then you have to define centrally where they match or what IDs or
Yeah,
what things are meant to be the same.
it becomes symbolically hard to refactor things when you try to rename it, or if it's named based on some kind of hierarchy. There's some coupling that is necessary. That's the tricky part.
Have you used Java Spring?
Uh, Spring Boot. Yeah, I used Spring Boot back in the day. Very first
But Spring
internship.
the beans there you can like annotate things that will get matched to classes you've declared in places. But
Yeah.
it's so easy to forget to do that, and then it's like missing bean, and that's the sort of like you can get this like really things that you don't always want implicit. That's the problem. You don't always want implicit. Implicit means that you don't see it. Implicit means you can't control it.
the
This
the
idea that
Sorry,
yeah.
go for it.
And I think declarative actually means implicit in some sense.
Because you have to
Declarative
you can't declare
it
everything,
means
right?
you get the behavior without saying that writing out the behavior. That's like declarative, right?
Mm,
What you
mm.
want, not how you want it. So declarative means you can't see this, or you can't see part of it. Like declarative control language is almost like a anti-pattern.
Mm.
So I'm sort of being facetious about that, but you don't. At some level, you want to be able to see what you're doing. Anyway, we have a look at this. So this paper, the notes don't go into the other syntaxes. Do you want to have a look at them briefly?
Yeah, should we talk about the second, just the module composition in ESTEREL? Do you think that would
We
be
can do. I
helpful?
was trying to remember how it works.
Um, well,
I think there's just like a parallel. There's a parallel
yeah,
reason
it's
to it.
pretty much just there's a second. So essentially, the part B of this figure defines another module called speed supervisor. It inputs seconds and meters and outputs whether something's too fast. Um,
Yeah.
and essentially, what I believe it's doing, it's keeping track of the current speed, and in or concurrently, different from running in parallel. Concurrently, we're running our speedometer, which we previously talked about, and then we're running this little code that as the speedometer emits a speed output, we're taking that speed output and we're saying, hey, is it faster than the max speed? If so, then we're going too fast. That's all this is doing. And it sort of just shows how modules can be composed together and additional behavior added on. Um,
Yeah, and they've got a couple of like some supervisor type things as well.
yep.
It's just sort of throw throw and exit and go to other parts, which I don't think we need to dive into, but it starts to resemble. Yeah, you start having sort of things like activities, but yeah, notice how the signal speed is declared outside of the color region, so
Yep.
actually get access to both to that. I guess in the same way that a event sent to a state chart is broadcast to both regions, but when you have an activity in the state chart, that's usually like almost a separate. SEEREL doesn't really have that notion. Like it's everything has
Mm,
access, as I understand it, to all the signals. At least maybe you can declare sub signals, but the activity, the equivalent of an activity in a SEEREL, just has access to the outer scope.
yeah.
You know,
Yeah. I like the bracket notation. I've been
that's
thinking
quite nice.
about I'm just very nitpicky, not nitpicky, but very uh, maybe it sounds trivial, but I like that the brackets represent like these things are running like side by side, just like the straight lines and I don't know using that particular syntactic notation. I like that. Plus
Yeah,
um, parallel sign as well. So
so, yeah. There's a lot more in the SEEREL to
for
unpack,
sure,
and there's a couple of good papers there, but I think
just
I'm not so worried about the syntax, and because the point of this paper is really the comparison.
yeah,
I think we maybe just briefly go into, so you'll need to switch back to the main paper because it,
yeah.
and then just briefly look at the notations of the other ones, and then I think we come back to this one, also the one you're just at, which goes into like compilation. I think it's got a really good overview. It gets mentioned in different parts in this other paper, but if we go straight to, I think Lust,
Yeah. Here's a counter. Um,
yeah. Do you want
uh,
to actually go up a little bit? Because it goes into the synchronous languages and it does an overview of those. And there's an interesting diagram which I think really gives the
oh, this one right
idea
here.
behind all of
Yeah.
these. Yeah, and I think it's really the key.
So here's how I think about the visual graphical notation of a sterile and state charts. A node like a box represents a mode that you're in, and a wire represents a change between modes or states. Which is very different than what the same things mean here. So here, a node visualized as a circle represents an operation that you do on the data, and the wires represent the data flowing through the nodes. So here, the boxes represent a transformation that's happening. Um, so
Yeah,
they have a very like even though similarly they're graphs probably nested into hierarchies and are composed into hierarchies or whatever. The wires and boxes mean very different things. Um, I don't know if there's anything you wanted to touch upon here, but anything else you
well,
want to touch
I guess it's
upon.
sort of like the concept of what time is, how
Mm,
time is represented um, in these, and it's kind of this is a diagram where I was like, okay, this is really like event chart semantics. We're really going to have to think about this. Sort of
mm,
like, and you can imagine if you start having concurrent diagrams
yeah.
where they can maybe split out and join, you have to think about, do you do like a depth first or a breadth first sort of if you're splitting out, and then A and B are doing things. What if A finishes, does then that have to wait? Are you sort of like, you have wait blocks so that conceptually a parallel region finishes at the same time,
Yeah.
all that sort of stuff.
Synchronization.
And it's synchronization is the word. And then also here it talks about how you can actually have some of these inputs on on different clocks,
Yeah, yeah, yeah.
which is like interesting. So it
It's
could
not
be
really
getting sort of like, yeah,
it's not really visualized. At least in the notation they give here, which probably wasn't isn't any like official notation, just like a helpful diagram. But yeah, like there's timing aspects that are really hard to visualize and articulate in a in a strictly visual notation.
totally.
Totally, yeah, totally agree with that. Hmm.
So yeah, should we go have a look at Luster
Yeah, yeah,
briefly?
yeah. Here's a counter. Let me just check if there's any. Yeah, no. This is the example they give here. Um, to me, the thing that stands out is this concept of um, on a new tick, this node will reevaluate, um, and you can reference the previous values in this node. I think that there's something weird about that in my head compared to how like as I think these data flow languages conceptually in my head are very much spreadsheet like. Maybe
Yeah,
semantically they're a little more rigorous. Like spreadsheets don't really. I don't think spreadsheets really convey like these things are all happening. These concurrent computation is all happening synchronously. Like I don't think that's as important in spreadsheets, but um, to me, like yeah, the whole thing of like accessing the current count but also the previous count. Um, through I don't know. It took me a little bit to like wrap my head around that. I don't know if that was similar for you.
yeah, just made me think that there's an interesting. If I know that diagram wasn't a Luster diagram, but that visual, some of these languages seem to have a very natural visual notation and a very
Yeah.
dense or just tricky textual notation. Um, when you're just trying to think, it's the self-referencing aspect I think is tricky, and ESTEREL actually had this too, I guess, with the broadcast. It comes back to broadcast really, because that's what you're talking about, right? This reference of like ticks and stuff is sort of like signal broadcasting, or
Yeah.
um, and I just find it so hard to parse when I look at the text.
Yeah.
How things are being referenced and where they're going, because it's describing almost the flow is sort of central to the understanding of the system, but it's the textual representation really doesn't convey it, where things are coming from and when they're going, because they're in different sections, and so you have to like map between them.
Yeah. Yeah. That as well. Like you're sort of talking about the return statement
Yeah,
and like count is actually defined down here, and then yeah,
yeah,
it's like you have to like go back context switch back and forth between the different parts.
yeah. Although I will say that that sort of definition or like a header section I've seen in a couple of these languages, I think is interesting, and it sort of defines an abstract component.
Mm-hmm.
Again, is it VHDL, these sort of circuit languages, you do that where you define an and you'll define like input A and B and then output C as the pins. And that's like an abstract definition, and then you can go and implement them. And in the implementation, you can actually drag in existing circuits to if you want to build a composite.
Yeah, yeah, yeah,
So I think that idea I think is like definitely something I've been thinking about for event charts. The original sort of idea was around circuit design. So having like an abstract header and then having a block that is the implementation, I think is interesting. And the sort of wire metaphor is also something, or flow is 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 interesting. But I do think yeah, the gap to the textual notation is tricky to manage.
Yeah.
Um,
Do you know what the arrow means here? In it, arrow, and then you sort of have the crux of the logic. At least that's how I'm reading it.
I think it's some initialization. Like you can define a precondition or like a pre-value before a tick has happened, and then everything else is what happens on each
Right,
event,
because
I believe.
in this language there's a concept of nil if
Mm,
before the first tick.
I believe
So
so.
like on the first tick, this value is actually nil. That's what I sort of remember. So maybe count is in it before the first tick.
Yes, I believe so.
Okay. That actually makes sense.
Yeah. Just trying to think if there's anything else. Again, obviously there's a lot that you could go into. And the paper itself goes into verification, but I
Yeah.
think we save that for the notes.
Yeah,
Um,
there's it's very limited syntax, but I think the most important part is this like pre referencing the previous values that define the relationship to this like nodes
yeah, as
computation.
yeah, and it's sort of like how each notation deals with broadcast almost seems to be like the
Yeah.
crucial. I guess how it defines the concurrent regions and how it defines broadcast. They're sort of because they're the two parts of the synchronous, right? We spoke about how synchronous languages are trying to have deterministic concurrency. So those are sort of the two keys.
Yeah. I thought this was a really interesting statement right here. Um it's sort of just saying that like the thing, and it sort of gets into verification, but the things we want to prove is that bad things never happen. Like how can we
Yeah,
guarantee that certain things will never happen? It's just as important as proving certain things will happen. um,
yeah. It's sort of like, well, we want to make sure that somebody can never make a payment twice, right?
yeah.
That's the key part. Yeah, yeah. It's like via the negative. And actually, they go into here what I was talking about with like an observer, which is how you can. It was actually right below that highlighted section. An
Oh yeah,
observer
yeah,
is
yeah,
used to verify. Yeah. And so that's like one method of verification, and you can use all of them. It's like
yeah.
exhaustive simulation. Was there another highlighted part above there that you had?
Oh, just very basic definition. Data
Yeah,
travels along
yeah,
wires. Da 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 da.
yeah.
Um, yeah, that
Just had
was
a thought that
all I had.
composition. I wonder if it's maybe by definition composition in these languages is hard because you need to preserve the properties
Yeah, yeah, that's a big
because of the way
tension.
they preserve the properties. Yeah,
And I feel
like you
like
need. Yeah,
the way
sorry,
you could compose nodes together, right? Like that's
yeah,
important, but it can't. I feel like there's like a constraint where it has to be like composed statically. Like you have to know the composition ahead of time. That's my. I don't know how
yeah,
confidently I would say that, but that's my the trade off maybe.
yeah. Also comes back to the idea of like what are you modeling, and if you're modeling hardware, you don't really have extra things just pop up
Yeah,
dynamically, which is a big
true.
difference.
Yeah, yeah, I agree.
Um, so
Um, that's all I
yeah, I
had
think
on this language.
yeah, I think it goes into stuff that sort of applies to all of them, but it gets covered in the notes, so we can just go into briefly look at signal as well.
Yeah,
Yeah, relax signal.
we can come
Great.
back to this probably. I thought this was an
Uh,
interesting aspect.
yeah.
Is there an example here? Is there a good example? I guess
I thought it was above. The first wasn't right. The next page above.
next
Oh
page.
yeah, so that example there um,
Right here?
with the above, just above that in the same page. Um, so it gives you like the mathematical equation of a filter and then how a
Oh,
signal does
right
it.
here.
Yeah, which is like it's very mathematical, right? Like
Yeah.
almost like they tried to be able to write it out.
Yeah, just a
Eh,
set of operations doing some math.
Yeah, pseudo operations, and then the next one is like an on-off.
Yeah, honestly, I didn't
Hard to
fully
pass.
understand Signal. There are at least some of the examples they provided.
Yeah, well, if you have the next page, I thought there was another one just right at the start. Maybe it explains it a bit more.
Let me check
Above, sorry,
the.
above, sorry. By next page, I should have said previous page.
Oh,
The other notes don't have anything. Or is that not
here's a
signal?
statement.
So, yeah, that statement like notation of equality of clocks. Almost
Hmm.
like they can be like varying in time, and then it's like okay, that is this instant. It's an interesting way of synchronizing, right?
Yeah, it doesn't
Sort of
fully make
like
sense to me, to be honest.
I guess it comes back to the synchrony. I understand signal released as well. Um,
Yeah.
so signal involves like relations, constraints. Okay, clock-based constraints. Interesting. So I guess it means like at certain points these have to be true, or these are guaranteed to be true.
Yeah, but not always, right? Maybe that's what they sort of mean by relaxed here.
Yeah.
It's
So
like
like
only when you want them to
if they
be.
aren't at the synchronizing, no, if they're not at the synchronization point. So I guess like with a mathematical equation, if you had two statements that are true, but you have to actually imperatively change the values to get to the next state. During that process,
Yeah.
the relations aren't true because you're changing intermediate values.
Mm,
But once you get to the next clock, then you sort of settled. So it's sort of this idea of like a trend. It's like the state chart equivalent of a transition from one settled finite state to another, and in between, it's in this intermediate processing
yeah.
state. And that seems like but they do it via clock, and it's more like it's more value based or variable based rather than state based.
Yeah. Hmm.
That's quite interesting. Okay, should we pop over to the notes because they have some interesting parts and sort of like compilation, which I
Yeah,
did
let's
want to
do it.
touch on,
Yeah,
and then we'll finish up
just
there. I
let
think.
me check anything else here. I don't think I had any other
So
notes at the end. It was pretty.
yeah,
I was interested. It was interested that there was, um, a group around the time this paper came out that was trying to, um, create, protocols, formats, shared formats between, among all these synchronous languages. Um, I
yeah,
did think that was interesting. I did not know about that, and that's something I sort of want to read more
yeah,
into,
totally.
because that interests me a lot. But yeah, let's go to
Yeah,
the other paper.
I'd love to speak to some of these people too.
Yeah, I agree.
Do you reckon Harel would get on a
Get him on
call?
the. Yeah, that'd be funny. Let's see. I think you were interested in the end around here. Verification or compilation?
Yes.
Generation?
Let's see. Give me a sec where I got to. So yeah, compilation of synchronous languages. So yeah, they go into this like analysis. So most of the languages seem to have some sort of compilation where they can reject ill-formed programs.
Hmm.
Because the example. and LUSTRE of like loops that could be problematic, or just statements like x equals not x.
Yeah.
Um, when in LUSTRE that doesn't make sense because it's not like an assignment in the same way. It's like saying this signal is simultaneously the opposite value.
Yeah.
And ESTEREL has like similar things, as I said, like if you can have a wait, if you're waiting on something that can never happen because it's waiting for that block itself, then there's sort of deadlock. Um, so it says it's like easy in some of these languages to reject them, but in some of the like ESTEREL or state charts, it's easy to write these, and it's harder to reject them.
Hmm.
And like it mentions how state charts have to sort of deal with this semantically, which is interesting. It's interesting. These notations present sort of like a high level thing, and then it's like, okay, you sort out the problems that I've just created.
Yeah. Yeah. There's some. I don't know if it's a good term anymore. Accidental complexity.
Yeah, it's sort of like if you just think about it, not very briefly, synchronous and like broadcast is like just solves the problem, but actually when you go to implement it, it is the problem. It is like
Mm.
the core. It's like the core innovation that enables deterministic currency, but it's also where we have to put all the effort to sort of work out the semantics. Um,
Yeah.
okay, so there's a figure in the next page um, where it just has examples of like causality problems.
Oh. Figure. Yeah. 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 I don't think I read through these carefully enough. Let's do them right
But
now.
like the first, you can just look at the first one. It's like it's waiting for O to be present,
Ah.
and then it's got like emitting it inside that same block. So
It gets stuck.
yeah, and then module three is like present O and then emit
Mm.
present one and then emit two, and then parallel it's present if so present if one is present emit two, and then parallel if two is present emit one. So it's like
Yeah.
that what I was talking about before.
And they're very obvious here, but it's more about like if you're creating, some complex modeling the behavior of some complex system, like when do these arise? How can you identify them? How do you predict that they would happen or know that they would happen? And that's when it becomes much less obvious when these dependencies arise.
Yeah. Um, talks about how the first three get rejected because they're sort of clearly logical. The fourth one, it says it's a causality problem, but it's something that can actually work. It's that if I think it's I is present, emit S in parallel. If S is present, emit O, but I is an external input, so I don't see what the causality problem is. Maybe it's just causality is just how the parallel regions are dependent, but you can
Mm,
have some valid versions of that. Like state charts allow that in some ways.
yeah.
Yeah. But do, are there are there causality problems in state charts that are allowed? I think state charts are pretty, at least like something like X state is pretty loose, right? Like it doesn't warn you if you never emit an event. But it wouldn't. I guess state charts don't declare the inputs so
No.
explicitly. You do it at the TypeScript level, so you wouldn't know if you were never going to get an event.
Yeah. Yep.
Um,
But
yeah,
I I don't know. It's sort of like if you're expecting a sort of certain order of events, like it's not determinism,
mm,
but it's just like you expect a certain order of events, and if you don't get them, then the behavior isn't going to work as you expect. No, but it is working as
yeah,
expected, so there's like nothing wrong with that. I don't know. I don't see something as they present it here. I don't see as a big a problem, but maybe I'm not
No,
fully, I haven't fully thought it through.
I think you could say that, and you could say, why do you even need synchronous broadcast, right? Because every piece will be doing what it should when it gets an event, but how do you know what it's going to do? I think that's sort of the problem.
Mm,
There's it's causality in the sense that I want to be able to say this happens, this happens, this happens, and then this will happen. Whereas, yeah, you might be able to. The system is always doing what you coded it to do, but whether you know what that's going to be is different. I agree that this example I don't really see the big issue with. And in some cases, like you just have to say, well, just to be a bit more generous and say that it's allowed, but
yeah.
be careful about it. I mean, some of the like the notations in state charts they restrict multi like um interlevel referencing stuff like that, which is allowed. That can create just brittle code.
Yeah. But there's a certain trade off here. Like, how do you try to clamp everything down so the user never experiences problems at the cost of they can do significantly less? There's, I don't know,
And that's
there's
where
a
that
balance
it's where the
here.
real time system is like an important differentiator between what you want to do with the language, I suppose.
Yeah.
If it's like an airplane, you probably do want to restrict that.
Yeah. And that's such a good point, is like how, sort of depending on the systems that people work at, like, can we take these notations and can we use them in a more casual setting? Can we use get the benefits that we want out of them there? Can we use them in a more rigorous setting and get the benefits that we want out of them there, which might be slightly different, more rigorous, more formal? Um, I think that's a really interesting question to me. Um,
Yeah, totally.
that this highlights. And I don't know if there's if you wanted to talk about like verification at all.
The code generation part briefly is interesting to me.
Oh yeah, yeah, yeah.
With Lustre, they generate a loop, so
It's
they
like a
can
game
sort of
loop.
do
That's what it
a
reminded me of, right?
yeah, and they just I guess they do some sort of like topological sort, and then
Mm.
they just go through it in the order that you need to, so that the variables that are referenced later are available.
Well,
But
it's
then
funny because that's exactly how Excel
yeah,
works. Because I was making that little dummy version of Excel,
yeah,
one of my side projects, and so there's this article that was sort of was talking about topological sort in the context of spreadsheets, and then Excel currently uses topological sort plus dirty checking to like sort of lazily evaluate or optimally evaluate things, which is, I don't know, really interesting. But yeah, so and so I don't know, it's just funny that like these data flows, these synchronous data flow languages are spreadsheets in some very rudimentary way, with just much more rigorous semantics for how to on the timing of things, I feel like.
yeah. But what's interesting is the general equivalence. Like it goes into how the next part is about compiling to an automaton or state machine,
Mm.
the control part of the code. That's what ESTEREL did, and then LUSTRE, and I think they all have been able to reuse the same tooling. It mentions that they were sort of started to share tooling and everything, and
Yeah.
that's really interesting to me that they can all just compile to automaton, and those automatons are very well studied and known about how to verify them. You can just verify the compiled automaton. Um, that's like one of the main ways that they do correctness. But it also mentioned how still being compiled in circuits,
Mm.
like into hardware, they get translated into a data flow network.
Yeah.
Um, so it's interesting these sort of intermediate representations like automaton and I didn't hadn't seen a data flow network before. It's interesting to me that there's sort of like a common format that these can all be compiled to. And then might be multiple common formats like data flow network rather than a automaton. They might have different properties that you can or different analysis available to them.
True, true.
Um, it's very, very interesting to me that is going on.
Yeah, and but also that's what interests me so much about state charts was just like author them yourselves. There's something I like about that as well. Um, just in a more like concise manner.
Yeah.
I wonder
Yeah, so,
I wonder like what the trade offs there are. Like I wonder how big the autonoma that are being generated by these different languages, like how big are they? How big is the state space of these things for like complex programming languages, and like how does that affect verification and model checking and like testing and simulation? That's like something I like would love to know, but it's just really hard to use them, use these languages and maybe see the output. I'm not sure.
yeah. It I think they do touch on this actually. Let me see if I can find
Did
the
I?
trade-offs in like the different not in this paper, but
Oh, okay.
there was one of these ones I have to have a look, but it does go into like the trade-offs of the different compilation techniques. I think size of automaton was one, but they're actually quite efficient to run. Um, that just the size of them could be an issue. Um, one of the ESTEREL ones to say like the translation of
Mm,
serial programs to automata has a big advantage because it permits automatic proofs on the automata properties. So
mm,
yeah, that was sort of the point I was making. Um, I can so there's a few bits here about like distributed stuff. I think we just skip to that verification one and then wrap it up.
yeah, yeah, yeah.
Um, and yeah, I
Oh,
think
this
it's
is
just sort
actually
of
this was sort of related to what I was just talking about.
mm,
Slightly different tangent, which is synchronous. The synchronous compilation is saying is usually much smaller than uh, compilation for like asynchronous communication. I believe that's what this is saying.
yeah,
They're just less. Yeah, it's a smaller state space, less complexity, less proof, like less chance of error happening with the timing, with timed events, like events taking time to be sent. And I think that sort of gets to the essence of like what these synchronous languages are good for, like the constraints
yeah,
they're making and the things you get out of that. Um, it's like a pseudo concurrency.
yeah,
Yeah, I don't know.
yeah. That's a great term for it actually, pseudo concurrency. And that last bullet point is really it's sorry under the last bullet point, so into the next paragraph. The verification methods for synchronous programs are all based on the control autonomy. So that's like interesting that they're really just like a syntax sugar,
Mm,
right? Large automaton, and then the verification all happens on the compiled stuff,
yeah.
which is slightly different from state charts and state ML, right? Like you actually there's language analysis. I guess maybe not the correctness properties, not necessarily correctness properties that are being verified at the language level. It's more just like have you constructed
This
a valid
graph.
state chart in the
Yeah.
syntax of state charts, which is I guess a different thing.
Yeah. Yeah, I think they are different things. And what increasingly happens is, so I look at a language like peeling. So it's like you're writing a bunch of communicating state chart or state machines, um,
Yeah.
and because they know the entire system, they know all the components of that system, which are themselves state machines. They could do this like very complex analysis on on the entire system and formally prove different characteristics, which it's mainly used for like cloud server, mission critical cloud services, for example. Um,
Yeah.
but you need to know the whole world in order to like do that analysis.
Yeah.
I I don't know, but it just means you can use that notation much in a much more like you have to use that notation in such a like a controlled environment. You can't compose it in other execute run times or like different types of programming languages or whatever. And there's a big
Mm.
trade-off there with like how well you could formally verify something and how controlled then that environment has to be. And I think that's something I don't know. I feel like
It's
I lean towards the
yeah.
latter. Like I'd rather see like more composition and less formal verification, or at least that's what interests me.
Yeah, and I think that's the trade-off that can be made if you aren't focused on real-time systems, right?
Yeah.
Which is where the sort of like maybe we're apps interactive systems, or maybe that whole framing is a little needs to be updated. I think an interesting point that sort of relates to what you're saying is you were talking about that sort of observer pattern, which is
Mm.
like you write a program that checks like a model checker, and
Yeah.
it tests. So it's saying that it's on the 11th page that you can't actually do that in the synchronous language because you have to synchronize it with the program that you're testing.
Mm.
And if you do that in an asynchronous language, you actually change the behavior of the language by synchronizing it. Sort of like reminds me of the article wave duality, right? The
Yeah.
observation changes the thing. Um, so I think if it's just a synchronous program, you've naturally got points that you can check in the value of stuff and know what it is. And it's sort of also the value of removing time from the equation, as it were, because you can sort of just stop it or
Mm.
go into it at any point and it's like valid. Whereas if time is an input, and this is the problem when you try and mock anything, right? If you actually have a clock or anything that's running on its own, you have to find a way to externalize that to test it in any
Yep.
in a deterministic way. Um, so I thought that was an interesting point. And then it's got an ending section which nicely lists some other related topics. So it's like
Yeah.
program testing, how you integrate synchronous and asynchronous parts. Um, so yeah, you have extensions that modularize that or compose.
Yeah. I'm really
Um,
interested in this area, right? Like, um, particularly between like these data flow languages, you get
yeah,
derivation for free, and these I'd call it behavioral languages. Um,
yeah,
State charts in ESTEREL where it's like you get that. I don't know how to describe it, but you get that like event passing
yeah.
for free, that event processing. Maybe that's a better word. And
Mm.
like if you're able to combine the two together, then you can sort of get the benefit to both, in the ways that they best describe the different domains of data and behavior that they do. So
Yeah,
cool to see that shout out for sure. And then
yeah, and then
as
it goes into like combining the data flow and the imperative one
yeah.
and the complementary synchrony workbench. Not sure I'm familiar with that. I think I looked it up before last time I read this. And then the last part is it mentions lucid synchro, which
Mm-hmm.
is what we talked about, which is the Elm
Yep,
integration
asynchronous
for Elm.
programming. Infinite
Yeah.
sequences.
Yeah.
Yeah. Yeah, so it's sort of I like this section because it's sort of I think it just highlights the different impacts um, that the original paper and that this like paradigm of programming has and how it isn't. There's another paper we're going to talk about that touches on this topic, which is just like how this paradigm isn't it never really gained traction or isn't like highly popular.
Yeah.
To the point I don't even know if I'd consider it dead nowadays. I don't know. There are
Yeah.
remnants for sure and lineages for sure, but it's uh, a small paradigm. It's a small paradigm, but
Yeah.
it's funny because it feels so highly influential in so many tangential parts. That's what's
Yeah.
tough
And
to grapple with.
I think the domain is important as well. Like I think some of these languages, I think ESTEREL is still being used in some areas. The real-time systems are not
Yeah,
tend to swap out their code every year. So there's definitely areas of programming that is probably more important. Um, there's what's the one? I was talking to some engineers who use this like data flow tool for hardware programming. Flow something, node something. Can't remember the name of it,
oh
but I was like, oh, it's a graphical one.
like an actual tool or like a pair like
Yeah,
there's like
yeah,
node based or flow based programming, which is sort of
yeah.
similar to these data flow languages too.
But so yeah, definitely important work, even if some of the languages aren't really ever used.
Yeah.
Oh,
So
that's
I
pretty
know
much
one of the reasons that you were looking into these languages is you were concerned about event charts, sort of just like sort of just like I don't want to say copying, but like just having high overlap with like one of these languages. Do you
yeah.
how do you feel about that now? Do you, do you sort of see a distinction forming, or like is does
Well, I think it's hard to think through what it means. Like they're all equivalent, and I guess this is like a general thing about programming, right? Is like
but they're
at what
not.
level the equivalent, what is equivalent? Like you can all compile them to an automaton, and then the properties of the automaton apply.
Yeah,
But I definitely think at the how these languages differentiate around like syntax, I think, and also maybe a graphical representation, I think event charts are different. I guess
yeah,
when I read these papers, it makes me more worried is whether it can is could what I would like to do, which is sort of like a circuit modular um, composition where the pins uh, carry events rather than electrical signals.
mm,
Whether there's like a valid semantic that preserves like the properties I want, it's
mm,
more like my concern. I wouldn't say reading this has made me more concerned about that, but um, and then maybe it makes me more concerned or make me think more about like what class of programs things everything is valid for. Because when you start differentiating like interactive systems,
yeah,
it's like, is that a web app? And does that mean state charts aren't that good for web apps, or is that one of the reasons? There seems to be some sort of impedance mismatch there, and it sort of maybe makes me question like it's kind of nice to say, oh yeah, web apps are a reactive system, and state charts are for reactive systems, and therefore state charts are good for web apps.
yeah,
But then if you start getting into, well, it's not a real-time system in the same way, like it's not interfacing with hardware, what does that mean for what you want to do with the tools? That sort of opened up that can of worms, I think, in my mind.
yeah. No, that's hard. it's something I've always felt like pretty iffy about as well. Like
Yeah.
it's so hard to define like what it's useful for, and that's part of the beauty of it is like useful. I think it has like state charts have pretty are pretty like domain agnostic notation,
Mm.
but paradigm specific. That like there's certain things they're not good at any particular domain, but they're good for a certain class of problem. I
Yeah.
think there's a differentiation there,
Yeah.
but it's hard to
It's
know
also
what
you
it
get
is.
into a bit of the you get into the I mean, I've said that I think having a good sort of theoretical base is really valuable, but at some point you want to be developing against a real world problem.
Yeah,
But at least it works in that problem. So that sort of yeah, it's in isolation when you're not applying them to your own problems, it's really hard to think through.
yeah.
Um, but yeah, I think one of the things that I'd love to dig into is the basis of like the synchronous broadcast,
Mm,
because it seems very important to all of these notations. And
yeah.
there was a reference to Milner, who has like a it's called a calculi for synchrony, and that was like the reference for like the basis of the synchronous broadcast. So I'd be
Mm,
interested in that. So I suspect that's also what Harel was thinking about. And I am interested in some of the mathematical foundations for those things. Um, so that's like one sort of side, bit of research
yeah, yeah, yeah.
from this.
Yeah,
Um,
definitely. Let's. You should open an issue with the. Hopefully, we could find those papers and schedule a time to work through them. I know. Um, I would love to reread that I think it's Van Hoy paper on like what a paradigm is and what the different
yeah,
paradigms um, that we've up with so far. I think that is really important. The word paradigm in my head is like so slippery, but also it's like so important, and I'd love to like really talk through that, right? And I think today we touched on a very niche paradigm that
yeah,
isn't widely used, but has been highly influential. Um,
yeah,
and I think that those are like that's definitely a topic I'd love to dive into deeper. Um,
definitely. Like you, as you say, you start to trace these lineages
yeah.
and see how like the echo of something is represented in a modern day form, which I think is really useful. So yeah, I'll yeah, I'd love to create a summary document from of the paper.
Yeah, yeah, we'll
Which
definitely do that, and hopefully we can get some more people asking questions or just stating some comments or thoughts or
hmm,
ideas on what we just talked about for I don't even know how
yeah,
long. Um,
wow.
but yeah, let me stop this recording.
Cool.